So welcome everyone to this exciting webinar organised by IUPAC CHEMRAWN Committee, the International Younger Chemists Network, and of course Beyond Benign. I'm Fran Curtin. I'm a professor at Memorial University of Newfoundland in Canada, and I'm the task group chair for the project Promoting Chemistry Applied to World Needs. And so first, I'd just like to thank Chris for being willing to speak with us today, and I will just describe a little bit about this project for you all. IUPAC is the International Union of Pure and Applied Chemistry, and they work to serve the global chemistry community and the world as a whole through the advancement of chemical sciences and facilitate free exchange of scientific information. And this includes things like developing nomenclature, naming of the elements, but much, much more, including conferences and webinar series like this. CHEMRAWN is a standing committee of IUPAC. It stands for Chemical Research Applied to World Needs. And there's a group of us from around the world. There's a couple of photos of the committee there on various projects. And there's a couple related to webinars, one on entrepreneurship and one on chemistry applied to world needs, which is why we're here today. The International Younger Chemists Network is free to join. There's a QR code there you can use, and it's run by young scientists for young scientists, and offers networking opportunities to develop your leadership skills and mentorship. If you're interested in finding out more, definitely get in touch with them. They're a super friendly bunch of people. One of the activities, in addition to this one, that CHEMRAWN works with IUICN is the Global Conversation on Sustainability, which works to show how chemistry can be used to achieve the UN SDGs. Beyond Benign, who is a very important partner in this webinar series, has a mission of fostering a community that empowers educators to transform chemistry education for a sustainable future through green chemistry. They have the Green Chemistry Teaching and Learning platform, the Green Chemistry Commitment, and again, there is a QR code on this slide so you can find out more information, and there'll be a little bit more information at the end. So the main objectives of this project and this webinar are to show how chemistry can help us achieve the UN Sustainable Development Goals, and also target and highlight the IUPAC Top 10 Emerging Technologies. If you Google IUPAC Top 10, you can find out more about them. We're also, as task group members, working on short videos that can be used in high school and different educational settings to show how chemistry can be applied to world needs and build on some of the concepts in this webinar. So here's an example of the top 10 emerging technologies from 2025. And so electrochemical carbon conversion was highlighted that year, and direct air capture. So these are both related to CO2 sequestration and utilization. So important topics. So our speaker today is Professor Chris Slootweg from University of Amsterdam, and Professor Maurizio is going to introduce him.
Okay, thank you, Francesca, for your presentation of the project. And I have the privilege to introduce our speaker of today. That is a very good speaker, a very good professor, a very good researcher, and also a very good friend of mine. Chris Slootweg is a Dutch scientist. He was born in Haarlem, a beautiful town not far from Amsterdam. And he had very good trainer, very good teachers like Piet van Leuven and Michael Lappert in Sussex. He moves to England after his undergraduate education. And then he got the PhD again in Amsterdam with Kopp Lammersma. Kopp Lammersma is one of the, let's say, best scientists that I have met, working with phosphorus chemistry. And I remember that in that period I met for the first time Chris for a project that was named the SUSPHOS, that is Sustainable Phosphorus Chemistry. And there was an integrated training network funded by the European Commission. In 2006, he started his independent career at the University, at the Vrije University of Amsterdam. And then he became associate professor in 2014. And then he moved to the University of Amsterdam, that is a different university in the same town. And in 2024, he has become eventually a professor, full professor of circular chemistry. And circular chemistry is the topic on which you will talk today. I have just to read something about the mission of his laboratory that is very nice. Is to educate students at the intersection of fundamental physics, physical organic chemistry, main group chemistry, and circular chemistry. Apart to be an excellent scientist, he's also a talented scientist dedicated to technology transfer program. I know that he is the scientific advisor of a company that is, by the way, named SUSPHOS BW. Is a company that is dedicated to the upcycling of phosphate-rich waste streams to generate high-quality alternatives from which we can try to replace the product obtained from fossil fuels. He has got a lot of, let's say, an emerging scientist, a lot of grants. There is a list here. He has received the important prize. I will just mention the Alexander von Humboldt Research Fellowship. That is a very prestigious prize, and he got this as an experience in research. Today, we will talk about his research dealing with catalyzing, with the title Catalyzing a Sustainable Future, Radical Redesign of Chemistry for Circularity. I think that we have time for questions at the end of the talk, and so I give the podium, let's say the screen better, to Chris. Please, Chris.
Yeah, thanks so much, Maurizio, for the very kind introduction, the invitation, and I also would like to thank Fran and you for, the opportunity of sharing some of the work we do in Amsterdam. I'll share my slides at the moment. So I guess you can see my first slide now with the title. And if you look around, read the news, so there is ample to do, and ideally in terms of sustainable future, we need a radical change. And I really like to focus on that from an educational viewpoint, from a research viewpoint, as well as from an entrepreneurial viewpoint. Really the opportunities from my role in academia to push this change forward. On education, I'm actually proud to be the program director of this new bachelor program in the natural sciences, where you focus on the natural sciences connected to technology, so knowledge to technology, and connected to innovation, so the innovative needs for knowledge, but also in terms of applications. And we really designed this program mirroring the focus of Amsterdam Science Park on materials, on sustainability, on life sciences, as well as on AI and data science. So this is reflected in the 4 themes of the program, and I guess you can see the clear link to sustainability and circularity. That is one of the topics that students can specialize in, and I'm really proud because we designed the program from scratch. We also were able to include, theory on sustainability and green chemistry, toxicology, ecotoxicology, lab skills, obviously, and the application of that knowledge. So I've got a novelty. Today, the green chemistry commitment was signed. I'll send it to everyone shortly, but I'm really proud that from a University of Amsterdam perspective, we fully commit to the endeavor of also teaching students at bachelor level how to radically change our society. So let's move now to research. But basically, this is education too. It's the education of the students in my team, PhDs, postdocs, and together we learn a lot and like to share with our peers. And like Mauricio mentioned, the topics we like working on are connected to the main group, physical, organic, inorganic perspectives, and ideally always a strong link to sustainability. So why is radical change needed? For me, this is the strongest message to highlight that we need to do better, develop better chemistry as well, because even 2 years ago, Earth Overshoot Day was on August 1. And so after some months, we've already consumed globally the resources that were sort of allocated for that year. And don't ask me why this color coding is here green and here red, because this should be full in the red, the months of the year that we're basically exploiting planet Earth that is not sustainable. And so this is fossil resources, renewable resource, any resource we simply need to use more efficiently. So the paradigm in chemistry is you take a resource, you convert it into products, and then you stop thinking. So this scheme is something that also in research is not always coupled. So there is a strong focus on synthetic chemistry, but often it's decoupled from the environmental sciences. And I think there we really need to do better and connect the dots. And of course prevent pollution, but ideally close any cycle. So with the objective of net zero, this scheme is I would say not zero. So this let's say frustration from my side came also into play when writing this piece. The story reads actually quite well, but the title still could be a little provocative. But this really highlights that in chemistry, we use a resource, in this case coal, to get energy, but the byproduct is not ideal, and so we clearly need to do better in order to realize also and develop the technologies required for net zero. So this version of the periodic table actually also echoes this message and also highlights how we develop chemistry. If you think of the energy transition, then we start from an abundance of carbon in the form of coal, oil, natural gas, and convert it into an abundance of CO2 and methane and so on. So the resource side is not problematic, at least not in the coming decades, maybe hundreds of years. But at the waste side, there is obviously an acute issue. And the solutions that we try to develop in the energy transition basically rely on tools, on technologies that ensure basically require all the other elements of the periodic table. So a mobile phone, indicated in the picture. The complexity of the products are huge, and let's say in short, if we are using all those elements also in a linear fashion, then we may solve a carbon waste problem, but we create a multi-element waste problem next. So let's try to avoid this and let's try to really develop sustainable solutions. So at the moment, the impact of our linear thinking is visualized well with the concept of the planetary boundaries, where basically the picture depicts planet Earth. At the outset, I would say waste problems, global waste problems, and a color coding scheme, similar to a traffic light. Interestingly, some of the most dominant waste problems are connected to very, very simple molecules. Redox chemistry of carbon, redox chemistry of nitrogen, and there is phosphate, and all impacts biodiversity loss. And basically all the different waste problems can also interact. And so if we may solve an issue in some aspect, maybe we can create negative side effects in another. I'll explain that in a bit. More recently, the novel entities, basically the human-made chemicals, were also quantified and are also deep in the red. Why? Because quite a few contain persistent compounds like plastics entering the environment, PFAS, an important useful class of molecules and materials, not designed to enter the environment sustainably. And the other thing in general for these novel entities is that the testing and understanding of the function of all those molecules and materials doesn't keep up with production. So this is clearly something that we need to do better as well. So an example that there is some progress and very promising progress, and also from this complete life cycle analysis, we can learn a lot. So this is a paper by Steffi Hilweg, ETH Zurich, and she showed with her team that if we envision a net zero plastics economy in 2050, that is feasible. That is feasible if we consider alternative feedstocks, recycling, and so on and so forth. And she analyzed not only CO2 impact, but also looked at biodiversity and pollution. And the conclusion of that study was very powerful. So we can reduce the CO2 footprint, but at the same time, if we use our current system of biomass production, then this goes at the expense of land use, simply because we have way more land required to produce the feedstock. And it goes at the expense of pollution in the current system of producing biomass. The pollution is coupled to basically ammonia emissions from fertilizer use. So we can fix the CO2 issue of the plastics, but we need to do better at other aspects too. Now, another interesting one, if we think of the energy transition, wind energy, I mean, and especially in the Netherlands, is very popular, and there is a direct association with clean energy. But resources required to construct windmills have a very high supply risk due to, for example, the neodymium that is needed for the electromotor of the windmill. And so it's not that easy in terms of the solutions. There is more to it in terms of resources. And also if you think of electricity storage in the form of batteries. And so this picture illustrates, let's say, an old but classic battery. And if we look at the materials required for the storage of ideally clean electricity, it is copper, it's graphite, two critical raw materials listed according to the EU critical raw materials list. The electrolyte requires lithium and phosphorus, both critical raw materials, and the cathode requires lithium and cobalt, again, critical raw materials. So as a consequence, it's quite popular to develop other cathode materials that reduce the cobalt content, for example, the NMC batteries like nickel, manganese, cobalt. But actually the next step is to go to the cheaper elements, at least at the moment. For example, the lithium iron phosphate batteries. So lithium iron phosphate is the cathode material. But this paper really shared a very strong message. So this is from Fraunhofer Institute in Germany. And they highlighted that the current technologies available for metal refining, and thus also metal recycling, hydrometallurgy and pyrometallurgy, so really focusing on recycling, are not economically viable for the cheaper elements and the cheaper resources. And so it's nice and important to shift away to other resources to replace critical raw materials for maybe materials that are less critical. But the consequence is that at least novel technologies are urgently needed to be able to recycle also cost-effective these new batteries. So we need a much more focus on, let's say, higher up the R ladder, where we need to rethink the design, where we clearly need to design batteries for circularity, that we're not only able to make them once, but actually that we can keep the resources indefinitely. So the linear economy starts with resources, converts them into products, and then those products are at the end wasted. The circular economy is different. And actually, if you think of plastics, the first cycle, it is truly different if you would start from fossil resources or biomass or CO2 and make the exact same bottle. The difference for cycle 2, cycle 3, and cycle 4, and so on and so forth, in the ideal case, is that the product becomes the resource. And actually, if I use this bottle 10,000 times, then my biggest impact is that I constantly reuse the product and only need to make it once. And so that is, to me, the true power of the circular economy, where, of course, the design of those products are essential to allow ideally simple reuse, but ultimately also recycling. So, thinking of the message of Beyond Benign, the concept of circular chemistry was originating from teaching. So the paper we shared now 7 years ago started in class, me thinking about the circular economy and asking the students, okay, how is this circular economy, how is this wheel spinning around? And what kind of principles do we actually need to be able to enable such a circular economy? And interestingly, now I would rephrase some of the principles differently. I mean, if you think of collect and use waste, waste, that is the end game of linear, that is linear thinking. So even though we were thinking in terms of cycles, we still used nomenclature that is inherent of the linear economy. So this actually should say collect and use product, and really as a last resort, then please use waste and don't let this enter the environment. But actually, number one should be target optimal design, and then the rest follows. And so now it's actually quite nice to see the concept slowly but surely picking up, and also more and more research being developed in this area. There are now also 2 journals where every researcher can submit their work to, that has really a strong focus on circularity, simply to develop tools to use our precious resources more sustainably. And so this message was also echoed by CEFIC, the European Association of the Chemical Industry, and they also quote in this report, society needs to adopt circular thinking, and that is not easy. I mean, behavioral change is difficult, but also changing our way to think is not that easy. And there are many meetings in the circular economy arena that highlight, for example, okay, our supply chain is this and that. And then I'm like, okay, but in the circular economy, so I found this picture online, maybe there is a circular supply chain. So it should be a circle, but still it's linear, so it's a chain. Of course, it starts somewhere. We make products, and at the end we try to recycle them, but in the end maybe there is still and always waste. So actually the ultimate goal should be the development of supply cycles, where the manufacturing of the first product starts, the first cycle, and then I would relabel this as recovery, and then the manufacturing of the second product, the second cycle, is actually the recycling. And so manufacturing and recycling is identical. So it doesn't make sense to have a recycling installation that does not produce products directly, if you would ask me. And so this is something that we really need to develop. And pictures in general, again, in this case of the plastics economy, are there from, for example, the Ellen MacArthur Foundation. And what I find interesting is, if I plot the data from Steffi Helweg on this picture, is that this big big flow of recycled material has a reduced carbon footprint. And so fossil virgin production of a product versus the recycling and the production of the same product, but then using renewables has only a reduced carbon footprint by 10-20%. So I thought this number should be bigger. And so this is for plastic. So actually, this makes sense to keep resources in the loop. But in terms of energy, maybe we need to do better. Maybe we need to focus way more than this this scheme indicates on direct reuse. So we should ideally focus on this and do the recycling as a last resort. And why is recycling always essential? Basically to keep resources in the loop. And so this was published recently by Jean Barlange. And so if you close the cycle by mechanical or chemical recycling, different technologies are available and being scaled up. It costs energy. That is what I just indicated. But the objective is to reduce fossil inputs. And so in this case, again, for plastics. So applying this way of thinking, let's focus on nutrients. Maurizio mentioned phosphates already, so I'll share a short story about that, and then also focus on, let's say, reducing greenhouse gas emissions by the development of circular energy systems. So why nutrients? Of our key biogenic elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the only one that is indicated to become scarce is phosphorus, is phosphate. So there is a paradox: too little in the coming hundreds of years in the fossil mine and too much in the environment. And so this takes place everywhere, and as well as also in the US. I can definitely recommend this book. And this is not something new. And so we know climate change for decades. We know the disturbance of the phosphorus cycle in nature. It was published in Nature also decades ago. So we know that we need to act. So how? Another urgent reason to act is not only the resource is limiting, also in general in life, phosphorus is life's bottleneck. So we cannot substitute it, we cannot replace it, we urgently need it, indicated already by Isaac Asimov. So what to do? My favorite scheme in closing the loop is recovery. So the removal of waste or products, ideally from the system, and the development of renewable resources. For example, in the case of phosphate in the form of struvite, but this can be in many ways. And second step is recycling. And those two, the recovered material, the recycling technique, needs to be in full sync with the recycling method, that the recovered material is actually suited for recycling. So we thought, let's do this literally at the festival. So we went to a Dutch, popular Dutch music festival, and also included some citizen science. So it's sharing knowledge about circularity. So this is me. It is also doing an interview that we knew what basically would be donated, what the quality of the donations were, and we used that at the end for the analysis. And so on site, basically we had the best toilets close to main stage. So on site, we were producing struvite. It was a fun endeavor, I can tell you. And next, in the months after, we analyzed the struvite, and lo and behold, the quality of that struvite, we took this, let's say, as a worst case scenario, was still suited for recycling. It still obeyed the new fertilizer regulations, and actually it showed that we can do recovery, and we should be doing that way more, because then the material is always suited for recycling. So this case, closing the loop, is actually suited for, call it, off-grid situations, where also many countries can benefit from. In the Netherlands and many other countries, we have a grid, we have a sewage system, which is maybe not ideal. So households, industries, every wastewater also coming from toilets goes to the wastewater treatment plants. Disposable water is generated, and the rest is called a sludge. And actually, in some countries, France, this is directly added to arable land as a fertilizer. And of course, it's a fertilizer, but do you want this type of fertilizer on your land and on your lettuce? So maybe not, because obviously it contains, well, anything, including PFAS. So what is actually a better way is to do mono incineration of the sewage to create sewage sludge ash. Now, this is not a colorless material. It doesn't contain cadmium, like cadmium phosphate from the mine, but it also does not contain, calcium, I should say. It also does not contain any cadmium or uranium, but is also present in fossil phosphate. But it contains aluminium, iron, zinc, and so on. But the phosphate is ready to be recycled, which is the focus of Sysphos, the company. And so in my lab, we developed a process to convert renewable phosphates into phosphate products. And for a number of years, this is out of my lab and doing the full business development and scale up. And I can only dream how they progressed the chemistry that once was started here in Amsterdam. Marissa is still involved as CEO of Sysphos. And the dream is really that this installation that basically produces half of the sewage sludge ash of the Netherlands, that is actually will be connected back to this, at the moment, drawing of a plant that actually will do the recycling of the recovered material over here and do the recycling over here, so that we really and truly generate circular phosphate products, simply from waste streams, actually, which is in this case probably one of the most efficient ways of closing the phosphate loop. So that was nutrients. Let's go to energy carriers, and just want to share you my ideal picture of the energy transition. It focuses on electricity production, storage, and also it should focus on a smaller extent, on a smaller amount to hydrogen production, and then also storage to allow, for example, long duration storage, and also to allow transport. Now, if we can do that well, we actually can develop new use cases for hydrogen, for example, for green steel, for example, for heavy shipping, heavy transport, really one of the hard to abate sectors where hydrogen is definitely an essential ingredient. So how to produce hydrogen first, and what are then the opportunities? And typically I ask my students, okay, which one to pick? Which technology to pick to produce hydrogen? And obviously they focus on green for all the good reasons. The current state of the art is methane steam reforming, producing hydrogen together with CO2. The challenge, though, is simply thermodynamics. And so in the Netherlands, where I'm based, the energy price is relatively high. So we do produce hydrogen from methane steam reforming, but it's quite difficult economically to implement water electrolysis, not just for scale up, but simply because of the added costs for this technology, simply because you need to add like 6-7 times more power into the process. Now, and then if local production of hydrogen is not clean, or is expensive, then actually it becomes a possibility to produce hydrogen elsewhere, where the sun shines maybe 24/7, where the electricity prices are low, ideally. And then the case is, of course, produce it cheaply, then import it, and then use the hydrogen sustainably. So there are, in principle, a few options. So in this scheme, the energy density is in kilowatt hours per liter, comparing to diesel. And of course, you can liquefy hydrogen, but then, 20 Kelvin, with the risk of boil off, energy required for the cooling is 30-40%. That is substantial, but it can be done, and companies are working on this. Ammonia is another option. So Haber-Bosch is energy intensive, but the cracking of ammonia is also energy intensive. Let alone this is currently in the planetary boundaries picture a waste problem. So if we choose ammonia, we need to develop the system really well. And Port of Amsterdam, for example, said no to ammonia simply because of its toxicity. So safety related. So actually these other two options, using organic materials to capture and release hydrogen, as well as inorganic materials to capture and release hydrogen, become very interesting to study also from an academic viewpoint. So let's start with the liquids. And this is something we did together with Voyax, a Dutch spin-off. And we really combined all efforts, where obviously from the company side, the focus was on economy, on implementing it ideally in society, and from the research, I should say, from the natural sciences. My lab was focusing on making the carrier, hydrogenating the carrier, dehydrogenating the carrier, but all substances. We looked at toxicity, safety, reduce climate impact, as well as, of course, circularity, because if we can only use the carrier once, it's pretty useless. And of course, connected to the toxicity, what's the fate in the environment. And actually, we developed in co-creation with Voyax carriers, based on quinolines that are safer than diesel, can be stored at room temperature, atmospheric pressure, can be reused a number of times. So this is pretty promising. And the other interesting facet for this particular class of molecules is that they can release hydrogen catalytically at around 200 to 20 degrees. So then it actually becomes possible that if you would, retrofit a large ship with a combustion engine, that you can combust hydrogen, propel the ship, and use the waste heat of that combustion process, which is around this temperature, for the generation of new hydrogen on site. And so this is, pictures from my lab is to me really promising. Voyax is scaling this up, so they're now at liters, multiple liters at the same time of carrier and hydrogenated carrier. And this is basically their focus at the moment, 3 business cases, scale up of the carrier synthesis and hydrogenation and dehydrogenation. One of the options, I would say, for large-scale storage and transport of hydrogen. So the other is also something that is very appealing, is using inorganics, in this case sodium and boron, because upon their release of dihydrogen, not only the hydrogen atoms from the carrier are released, but also if you use water, half of the hydrogen atoms are released. So this makes it actually quite an efficient release mechanism, especially because of the fact that this can be done at room temperature. Now, the challenge, of course, is this step is easy. The recycling is more challenging, and that's why we worked on that process, or actually multiple processes to close the cycle very hard in the lab. And we've closed the cycle already for quite a few options, and are constantly modifying this. And actually, it boils down to, reinventing an industrial process of 75 years. So that takes quite some creativity and for us a lot of fun, but we're making some steps forward also together with these Dutch companies. At the moment, there is one prototype. This is a drawing of the ship of the board of directors for Port of Amsterdam, Neo Orbis, and actually the ship is in the water already, and hopefully in the coming months it will also sail on hydrogen using fuel cells, but the hydrogen comes on board from sodium borohydride. So these two examples I just shared really connect to the mission of circularity, design for circularity, where we actually can and should close the loop. Now, what about the many other products that are not so suited for capturing and recycling? Think of medicines that enter the sewage system. We for sure do not want to, separate them, analyze, purify them, and reuse. So how to do that? And for that, I just want to illustrate again phosphorus, but now organic organophosphates that are also applied as flame retardants. So the story starts now with this paradox. So a polyurethane mattress is flammable, and to reduce, or basically to increase fire safety, we add toxic flame retardants. So this paradox is to me mind-blowing. So of course, can we develop a mattress that is safe and circular? So first we thought, and are still working on the idea, that organophosphates are created via multi-step process, energy and waste intensive. Can we do better? Can we recycle renewable phosphates directly into organophosphates? How actually origin of life should have started. So we're trying to design processes that can do so. But the current organophosphates are not necessarily safe. At least they're to a certain extent persistent, being detected in the environment, and some also show toxic effects. So we use this as a starting point for a complete redesign of organophosphates that are currently detected in the environment, where we screened many alternatives and also evaluated them computationally on their biodegradability, toxicity, and so on and so forth. And only then we synthesized them in the lab and tested experimentally their properties in terms of biodegradability and so on and so forth, but also, of course, in terms of flame retardancy. And this looks pretty promising, actually. So the class with the ethylene glycol moiety basically passes the vertical burning test, as one available test for flame retardancy prediction and testing. And this is what we're currently continuing. We're focusing on this organophosphate that, although this one is phased out, still there are many derivatives that still you can identify as being hazardous. Where we conceptually focus on renewable phosphates as the core. We focus on the ethylene glycol moiety again, because that is also available from the biorefinery, like one step from glucose. The hydroxy groups are needed for increased water solubility and increased biodegradation. And still we stick to the flame retardant core being the organophosphate. But actually, is this the only way, substituting a hazardous compound for another one that is maybe ideally more safe? This example of a mattress it's marketed by Auping in the Netherlands, and it's called Niaga, so the reverse of again. This one I really like because it's created from 100% polyester, so no polyurethane, 100% polyester. Even the glue required is polyester. And because of the properties of this material, no added flame retardants are even required. So there is an inherent flame retardancy protection for this material, which brings me to the fact that at product level, we can and should redesign and focus on sustainability. Not only, designing one molecule for another or one material for another, but really look at the biggest impact we can have at product level. So how can we develop chemistry that is a little smarter? Obviously green, for converting resources to product. Obviously safe, obviously benign. But we need to look, beyond benign and focus on the circularity at product level, be it a building that should be more durable, a bottle that should be more reusable, or nutrients that should be recyclable. And so in all, the impact here is, of course, to use our resources a little bit more efficient. And with that, we're in full support of the Stockholm Declaration, and I'm more than happy to conclude my talk with the shout out to the editorial that we wrote also together with Juliana, because this for sure is the way forward, that we need to inspire our peers and as well as our students in class. So thanks a lot. I'll stop sharing and looking forward to the discussion.
Okay. Thank you so much. Thank you so much for your lecture. That is very inspiring. I guess that you have touched a lot of points that could be of interest for this, for the people attending this lecture. The lecture seems to me has been very inspiring also because really makes that has been a new perspective of what has been considered the sustainable chemistry. So sustainable chemistry is essential, is important, but there is much more to do. And the idea to move towards a fully embedded circular chemistry is really an important concept that is certainly inspiring your work and probably will certainly inspire the activity of most chemists around the world. So I guess that I am not very practiced with this kind of now of discussion, but I would like that I have seen that there are some questions. I have read time to time some of them. I ask also the help by Juliana and Francesca. And for example, I noticed a question raised by, Matteo Oleas. Matteo Oleas is correct, the pronunciation. And is working about, let's say, pharmaceutical compound. I read the question. I work for a company called Ovomass SAS. We transform eggshells into calcium citrate, that is pharmaceutical grade. A pharmaceutical compound focused on the circular economy. We propose an alternative to calcium citrate obtained from mining, which is, of course, not a reliable way to take the problem when there is some alternatives. And the question that arises is about the possibility that there are international funds that could support this kind of project. This is not just only the funds, I think, but only if there is a sort of international consortium that can help small companies moving steps towards the right direction. Maybe that you want to ask to this question, for example?
Yeah, thanks a lot, Mauricio. And this is a really important one. And so in general, doing something new, at small scale, also at industrial small scale, always costs more than the existing large scale infrastructure and so on. But ideally, and that should be the objective, is that, as I indicated, in the circular economy, we use our resources and products more efficiently, and thus it also should be cheaper. And so the objective of the novel chemistry that also Matteo is indicating should be cheaper. Otherwise, it's difficult to take off this new direction. Typically, it would be nice to start from local funds. I mean, from a Dutch perspective, the circular economy is already quite popular. So there are always, different kinds of funding schemes to do so. But ideally, at industry scale, the return on investment should be there if the right chemistry is being developed. And this is sometimes, really looking from a supply cycle perspective. Not easy changing all the optimized supply chains for supply cycles. But if you can start from a resource that has, let's say, a negative value and convert it into something valuable, like we did for sewage sludge ash to phosphate products, that is a really good starting point.
Yeah, they say that Dutch is a special case in general by considering this kind of special attention that your government and your people has toward this kind of problems. And another, I think, interesting question comes from Stan Selig. It's about recycling of water. And our colleagues is saying that this is also very important, but ignored sometimes. Water in the next oil crisis was the title of my past symposium. Wastewater disposal is a growing global problem. We must minimize wastewater production. And I would like to add the fact that water is not generally so innocent as it can be considered, because once polluted is dirty water. Please, do you want to comment this important point as well?
Yeah, absolutely. And also there, if we think in terms of, the product, let's secure clean water, how to do so, we simply need to develop new technologies or need to apply existing technologies. In this respect, the Netherlands has always been a country that was, let's say, fighting water. We live half of the country below sea level. So we've never been conserving and collecting water. We've only been, getting rid of water and do it safely. So in terms of, our climate situation, also here we need to preserve clean water and collect storage systems and even more so focus on the purification. So I don't have a direct answer, but it's clear that every single resource, including water, is very precious.
Thanks. So I see another questions, but there are many, of course. Maybe that these questions can be collected and sent directly later to you by Juliana or Fran or Francesca, and you can reply later. So another question that I think is very interesting is how much energy, this came from Mumbai, from a colleague from India, Shraddha Tiwari from India, Mumbai. How much energy is required to incinerate the sewage sludge? How does this compare to the current cost of virgin phosphate extraction?
Yeah.
Could you please discuss a little bit?
That's a very important one. So in this case, it's basically how to clean up the phosphate waste from the sewage treatment. It's basically, the conversion to ashes is energy neutral. So it contains a bit of water, so that's undesirable in terms of energy, but it contains organics that you can incinerate with the objective to purify the sewage sludge. So it's energy neutral, and obviously, carbon capture can be installed with also some scrubbers if some other waste streams are being emitted. But the objective is really renewable phosphate. We have in the Netherlands truly, all the sewage is incinerated that comes from households. So the recovery is there. Again, it's not ideal. I mean, it's not a colorless material that comes out at the end, but it's the system that is in place now. And that's why we focus on that largest stream of phosphate that can be recovered to do the recycling.
It's a big problem anyway. I see another one. I think that we can still stay a few minutes more, if it's possible. The question came from Blaine Fils and moved the question from let's say, technical viewpoint of the problem to a more general viewpoint of this big problem. And the question is, I fully agree that the behavior change is a key step to implement lab and pilot circularity to society as a whole. What advice would you give for how we as scientists can also act as translators for policy change at the government level? This is a huge question because it depends largely from the kind of politics that you have to face with. But please, what is your opinion on that? And your experience, I guess, in the Netherlands and the European community as well.
If there is a period in time that the preservation of resources and the reduction of dependency on other global countries in terms of resources, it is there, it is now. So if countries along the globe can be circular in essential resources, they don't have to be traded, so they won't be wasted. Critical raw materials is an important topic, and that really highlights that in every nation we need to develop recycling industries that are production industries of the essential products, fertilizers for food, batteries for electricity storage, and so on. And again, if now is a time that makes it clear that we need to change, it is there.
Okay, this is a difficult question. Anyway, so
but in terms of convincing, also politicians,
yes.
Well, I mean, the need for more circular approaches. I hope in every country there is a strong foundation for that.
I see that at the end of the list of questions there is one very long question.
I don't think we have time for that because I know Beyond Benign just has this one
okay,
license.
just to close the connection probably. Yeah. So this question, like other one, will be delivered to Chris, and I'm pretty sure that Chris will be happy to reply either personally or just through the organizers. So let me close by congratulating again Chris for his really brilliant presentation and for the patience to answer to all the points that the people has raised. Thank you very much, Chris.
Yeah, thanks a lot, Mauricio.
Please, Francesca.
Yes, so George has gone ahead. Sorry, Fran. Do you have anything to say, Fran? We're good to go.
Okay, let's close everything.
Yeah, I just have a few slides. So first of all, Chris, thank you so much for being here. Thank you all for being here. The discussion in the chat was amazing. To see people from all over the world joining us. It's super.
Yeah. How many people were connected at all?
We had 78 people, so that's super exciting. Thank you all for being here. And I just have a few slides to promote our next webinar series that we have here at Beyond Benign, called Green Chemistry Connections. So on April 15th, you'll hear from Francesca Curtin and also just from the BRC, and the QR code is going to take you to our registration page. And also, if you want to continue the conversation, please join our Green Chemistry Teaching and Learning Community, our GCTLC platform. It's an open access place where we try to get the Green Chemistry education community together so we can collaborate, upload resources, and connect. So that's all I had from my side. Chris, I saw your email. Thank you so much for the Green Chemistry commitment. I'll be in touch. Super excited. My jaw dropped whenever I saw the image. So I just want to thank you so much and all of you for being here today.
Ciao, and have a nice day,
thank
everyone.
You, Maurizio.
Ciao, ciao.
Thank you, everyone. Good to see everybody. Thanks for all the questions.
Thank you, Ben.
Thank you very much.
Ciao, Francesca. Ciao, Ciao, Silvia.
Thank you, Silvia. Thank you, Chris.
Thank you. Bye. Thank you, Chris.
Have a nice trip to the United States. Take care.